Okay, we're recording now. Thank you. Good morning, everybody. We are going to talk about TR-55 today. That's Technical Release 55. And we will go ahead and get started in the presentation. I'll share. And TR-55. Why would we use TR-55? The rational method is a very common method, and we've talked about before. It's good from 0 to 324 acres. And then a TR-55 takes off for the bigger watersheds around 200 acres up to 5,000 acres. And then for the biggest watersheds, there is another version. It's called the regional regression equation, and that's in the Highway Design Manual. And that would be for big watersheds such as rivers. So today we'll talk about TR-55. And what happens is the rational method seems to work pretty well up between 0 and 200, and then at closer to 300 it gets a little more rough. And then TR-55, there's kind of an overlap there between the 200 and 300 acre area. And at that point, I recommend you do both calculations and then use your engineering judgment to select which queue is appropriate. It's not necessarily the biggest queue or the smallest queue. It's just as you, as the engineer, going through both sets of those calculations, which one do you think is most appropriate to use? Um, and then when you start getting onto the bigger watersheds over 300 acres, then you just get into TR-55 and just stick with that. Rational method might take you a day to perform the calculations, and TR-55 might take you 3 days to do the same type of calculations. So it's a little more lengthy in the process. So I'm going to go ahead and open up the manual here. So I attached this TR-55 manual, and the spreadsheet that I'm going to show you today is works side by side with this manual. It's broken up into several chapters. The ones that you'll focus mostly on are chapters 2. Let's see, we'll get into chapters 2 here, which is the soils chapter, and then chapter 3, which is the time of concentration, and then chapter 4 are the Q calculations. And then so you can go through the chapters, and it would give you the instructions what you need to do in order to complete the calcs. And then in the spreadsheet that I'm going to show you later, it's going to refer you back to this manual occasionally to look at to select the runoff coefficients, for example, that you'll need. And so you'll come back to this occasionally. I'm going to take you to page 153. And this is the worksheets that go along with this. What they've got it done set up for is worksheet number 2 is chapter number 2. So when you go to chapter number 2, you've read all the instructions on what needs to be done, then you can come to this worksheet and practice it. I do recommend that you practice by going through handwritten calculations at least once so that you understand everything that's going on in the background of the two methods that you'll learn about. Um, you'll also notice that the spreadsheet that I'm going to share with you is laid out very carefully, very similar to this, so that it's easy to follow along with the manual. And then worksheet number 3 is how we calculate the time of concentration. And the worksheet's originally set up that you could actually do 2 time of concentration calculations through here. And in the spreadsheet that I'll show you, we have it set up for 1 set through here, and then this is set up for notes. And then here is where we calculate the Q. So these are the worksheets, the spreadsheet that I'm going to show you is based on. And if you have anything that you're uncertain about in the spreadsheet, you can always go back to this manual. It gives you all of the formulas that go to the spreadsheet and all of the instructions on how to use it, on how to do it as well. Okay, go ahead and open the spreadsheet. Now the spreadsheet that I'm going to show you, when I was brand new with hydraulics, I was trying to learn TR-55. And after I did a few of them by hand, I got really tired of pounding the calculator, boom, 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 all the time. So I sat down and built this spreadsheet. And I was very new at this, so I built this spreadsheet so that I could follow it through the process. And so all these little side notes that you'll see in here were intended for me to, as reminders of where the information came from and where it goes to. And since I've built this, others have discovered it, and it's been kind of shared around. In the previous presentation, I emphasized when people share spreadsheets, be very careful of what you accept from them and then just blindly use. You want to make sure that the formulas are accurate and nothing's been accidentally changed. This is the spreadsheet that I see get tweaked um, often and see mistakes pop up in. And so just be careful that the formulas are what you want. Back when I put this together, we used to have to calculate the imperial method and the metric method. So I put together a summary sheet that used to have two boxes here, one imperial and the other was metric down below. And once we dropped the metric system, then I just dropped all that out and stuck with the imperial summary. So ultimately, these are the magic answers that you're looking for, the Q. And then there's a little check here that takes place and it's going to say OK or see note below. And down here, it'll refer you to a note. If you get this note, it's not that big a deal. It's nothing that's going to stop you. It's just warning the user that you were not able to plot this on a graph and you had to go to some default values to use. The blue areas are input areas. The white are calculations or permanent data that stays in the spreadsheet. So all you'll really have to do is is fill in the blue areas. Just starting across the top, the project, the EA, who's done it or who's working on it and the date, and then the checked by, if you get it checked by somebody, and then any kind of description that you have of the location that you're looking at. And then is it the present condition or the developed? So existing or proposed? And that's all you need for this. And then these will be carried through to this title header here will be carried through to the other sheets for you. And going to the first worksheet down here on the bottom, worksheet number 2, you'll notice it looks familiar. This is the one that we use to calculate the soils for the project. And you're going to need to go to the NCRS website to get the soils. And I provided a link for you in that. Let me go show you here. Under the links, I provided that soil map. When you go to the soil website, you're going to want to download the soil map, and there's a couple of different ways you can get that out of there. Basically, you can get a big square area of interest, download everything, including extra beyond your project limits, and then you'll have to trim it down. Or you can take the time and input a shape image into the soils map, and they'll cut the soils areas for you perfectly. And then when you bring it back into your microstation, it'll be laid in there, cut, and you won't have to take the time to do so. I don't use this often enough to be able to tell you step by step how to go through the soils website, but we do have staff available that could help guide you if you get stuck. So go to this website to download the soils data. You're going to need, pardon me, ultimately, you need the soil group letter, A, B, C, or D for the soil area. You're going to download a map that looks a lot of outlined areas such as this. And then if you take the time to turn the watershed into a shapefile and send it over to the website, then it'll come back trimmed for you already. And if you don't take the time to do that, then it'll come with the soils shown outside of your watershed, and then you'll have to just trim it down. But ultimately, you need to be able to measure the size of the area. And these numbers are coordinate to the soil group. So the soil number 111, depending on the soil report you download, soil number 111 will give you a soil group type, and that's what you're looking for. And that'll be translated in the PDF documents that you download from there as well, the soil report. That'll tell you what the description of 111 and then the soil group type A, B, C, or D. So once you get the soil group type, the group is what you're really interested in, the C, and then you come over here to the TR-55 manual and go to the tables 2-2, 3, or 4, and then you'll select the curve number for that. And in this case, we selected a 70. I'm going to blow this up a little bit. Hopefully you can see a little better. In this case, we selected a 70, and there's 5.2 acres for it, and then it gives you a weighted coefficient for the area. And then you list all of your soils in your watershed in this in here, and it'll come down, give you the total area for all of the soils, which should be the total area for your watershed, and it'll give you the weighted coefficient that it's calculated for that area. And in this case, it was a 70. And in this spreadsheet, I put in what I call a circuit breaker. This is a point where the engineer has to stop and think for a second. I didn't want to keep this automated. I wanted to stop so that you just had to stop and take a break and make sure it's working correctly. So once you get the 70 or say a 70.3, then you round it to the whole number. And in this case, we chose to round it down to a 70, say from a 70.3 to a 70, or round up, whichever appropriate, and then take the whole number there. Then you'll need to come down and collect the rainfall data. You'll need to go to NOAA Atlas 14 again, and then this is the rainfall depth that you're looking for in inches, not the intensity, not inches per hour, but depth. And you put the depth in there for the 24-hour storm across here. And I have provided a link to NOAA Atlas 14 for you as well. However, for the project that you're working on, I believe these tables have already been downloaded for you. You put that in there, and then that completes the soil data for you. And then going on to the worksheet number 3. This is where we calculate the time of concentration. Now, the time of concentration is the time it takes for the water to flow from the most hydraulically remote part of the watershed to the point of interest, the inlet of the culvert. The most hydraulically remote is not necessarily the furthest away. It's the location in the watershed that's going to take the water the longest to get to the to the inlet. So you're looking for the one that takes the longest time to get to the inlet, not necessarily the longest distance. And to get that, we're going to calculate 3 segments of the time of concentration. We're going to calculate the sheet flow, the shallow concentrated flow, and the channel flow. And in the sheet flow section, that is the first 100 feet. Now let me see, I think I have that here for you. So in the top of the watershed, the first 100 feet of the watershed, that's going to be sheet flow. We don't go any longer than that. And then after the sheet flow, then the next segment is going to be shallow concentrated flow. So sheet flow, there's no defined channels, there's no erosion, nothing like that. It's just sheet flowing across the land. And then as it starts to form little rills and little small channels and gather a little bit of depth to it, that's shallow concentrated flow. And then when it comes into defined channels, and you can see those on the quad maps, those V shapes in the contours. When you get to those channels, that's when you go into channel flow. So you have the sheet flow here, the shallow concentrated flow is the red, and then the channel flow is the blue here. And in your watershed does not have to include any, or it doesn't have to include all of these. You might be calculating the flow on a paved area that is simply 50 feet wide and it's all sheet flow. Or you might not have any sheet flow whatsoever and it goes right into channel flow. So you don't have to have all three segments. So the first segment is sheet flow, and that is just putting notes here. You go to TR-55 table 3-1, look up the description that you're going to use, surface description, and then the roughness coefficient that you're going to select for that surface condition. And then the length is 100 feet. 100 feet is the max. 300, this is an old note I should have deleted. 300 feet used to be, and it was changed a few years back. And then this column over here was originally intended so you could actually do two segments of calculations if you wanted to. And I've converted it just so I put some notes over here to help me remember where, or help the reader learn where I got the information from. In this case, it's 100 feet long, and I estimated the top of the watershed from the quad map and got the elevation of 1258. And then at the end of that 100 feet line, you estimate again from the quad map and use the best available data you have. In this case, the quad map was it, and I estimated it at 1240. And then the calculations take place. There's the 2-year, 24-hour storm. That number is brought over there automatically for you. And then the slope is calculated. And then here it gives you our travel time. And the travel time here for sheet flow, it does a little conversion. This is in hours. And in here it's 0.45 minutes. So in this one, that was really pretty quick. It must be rather steep in this case. So in a really flat area, the sheet flow can get into the minutes or even tens of minutes. And then after sheet flow, we come down to shallow concentrated flow. And that is now, on the quad map, you don't see the really well-defined V's, but you start to see the contours are starting to show some curves there. And the water's starting to gather a little more depth and form some channels, some very small channels. And that's the shallow concentrated flow. And we pick that up from the end of the sheet flow all the way down until the beginning of where you're going to define the channel. And that's how I find the length of the shallow concentrated. And here we go to, I need to point out the TR-55 method of calculating the time of concentration. If you go to the the TR-55 manual, it is going to give you different formulas than what are in this spreadsheet. The conflict is the Highway Design Manual has taken the TR-55 method and tweaked it and put some of their own formulas in there. And so when we have a conflict between the Highway Design Manual and another guidance manual, we use the Highway Design Manual because they have a specific reason they want us to use those formulas. So in this case, I'm not going to be using the formulas or all of the formulas from the TR-55 time of concentration calculations. We'll be referring to the Highway Design Manual. And in the first segment, it doesn't really show up. But in the next segment here, it starts to refer us to a Highway Design Manual for the ground cover, for example here. And so when we go to the Highway Design Manual, we'll select that from the table. And then the length here, you measure the length along that path you get from microstation. The top elevation on this one is automatically selected from the bottom elevation here. And then the bottom elevation on this one, you just hard type in. It goes through the remainder of the calculations for you. And then here it takes 11 minutes to get through that segment of the time of concentration. Now the travel time for the final segment is channel flow. Now in channel flow, that's where you can see on the contours, it's a channel. There's a V shape there. There's a channel. And what you're going to want to do is you're going to need to draw up a representative channel. So take a cross section of the surveys along that channel as close as you can get to it. And then if you can't get our surveys at that location that you need, then you'll maybe in a field review go out there and measure it, or take your best guess, however you define that channel. And then the first part of the channel flow is we're going to need to know the cross sectional area of the channel, and we're going to need to know the wetted perimeter of the channel. And in order to get those, we need those so that we can calculate the hydraulic radius. And in order to get these, we need to go back to our old favorite design cross sections that you've seen in the past. And then once we get to the design cross sections, you want to zoom in on the area that you're interested in. And in this case, we'll say the top of dike here, and the channel we're interested in is going to be right in here. This drawing a line straight across the top, that defines our channel. The red line is our channel down here. Now I'll get rid of the background. This is the only area that we care about in the channel. So this is the cross-sectional area of the channel. Now you notice I just went to the top of the channel. So if this is a V ditch, it's the same thing. You just go to the top of the channel and you draw that at the top. When in reality, the water might be flowing somewhere lower than the very top of that channel. And you might be tempted to go into a series of iterations and run it with the lower, run it at the top, find the water level, run it at that level, find what that level is, and keep going until you refine it. But our headquarters hydraulics department and highway design manual just say one iteration is enough. So just start at the top of the channel, do one iteration for it, and that's all you need. And so at that, we have the cross-sectional area. And then the wetted perimeter is the blue line right there, the bottom of the channel. Going back to our spreadsheet, it's asking here for the cross-sectional area and the wetted perimeter. And once we put those in, we come down here, what's the roughness coefficient of that channel? In this one, I happen to select asphalt. And again, I went to the highway design manual to get that. Here are the formulas that are taking place in these calculations here. And if you go to TR-55, I'm pretty sure that's not the formula they tell us to use. I'm pretty sure this formula comes from a highway design manual. And then coming on down further, we have the length of the flow. And usually you measure that in microstation. And then the lowest or the top elevation is copied from this elevation here, the lowest elevation on the shallow concentrated. And then the bottom elevation, you type that in. That's usually the grate elevation, the top of grate, or the flow line elevation of a culvert inlet. So that's the final elevation that you're looking for. And then it comes down and it gives another 1.51 minutes in order to get through this channel. So adding all of these minutes together, it's telling us that it is, adding all the hours together, it's 0.21 hours or 0.22 hours. And then we go to the highway design manual and it tells us that we use a minimum. So for paved area, we would use 0.083 hours. So that's greater, if we were paved, this is greater than the minimum of 0.08, so we would use the 0.22. And the minimum of 10-minute time of concentration is 0.166. So if that's greater, then we would use that or the max or the 0.166. So this is the other circuit breaker that I've put into this spreadsheet that causes the engineer to stop and think. It'd be real easy to put a formula in here to have it do it automatically, but this one, you stop and think, compare it to the minimum time of concentration, and also look and make sure that these times seem to make sense for what's going on. And then down here in the bottom, it just tells you the overall time it takes to get through there is 13 minutes. And that's it. That's our time of concentration for the watershed. Now, what if you have a channel flow, for example, and it's defined a channel off-site, and you can see it's coming down a really steep slope. And then as it gets to the bottom of the slope, it starts to flatten out and then comes on over for maybe hundreds of more feet before it gets to the highway. So those two dramatic slope, that dramatic change in slope, you wouldn't want to model that all in one column. You would want to model the steepest section in one column and then copy these formulas over to this second column. And then the flattened out section you would want to model in this other column, and then add the two of them together to get the total through this channel flow. Because the water is going to come whipping down that the steeper area much faster, and then it's going to slow down and go across the slower part much slower. And so just taking an average of the two doesn't really work out in every case. So in some cases, it's more appropriate to split those up. And that's what the dual columns were originally intended for. And I've taken over and used them for notes instead. Now, the final worksheet that we're looking at is how we calculate the Q. Coming down here, most of this information is copied over from previous parts of the spreadsheet. The acres that you have, the runoff coefficient or the curve number that you're using, the time of concentration for the watershed here, and then the rainfall distribution area. So 1A, you have a choice of 1A, 1, 2, or 3. And the way you find that, there's a map in the TR-55 manual, and I have that. Oh yeah, I'm sorry. I put it here for you. I added it here. Here's the map. Here's the different rainfall types, 1, 1A, 2, and 3. Most of our jobs are in this 1, but then there's a bunch in the 1A as well. Excuse me, in the 1A is most of our work, but occasionally we have some in the 1 as well. So you'll have to identify the location of your project here and then select the rainfall type. And then just a drop-down selection of what type it is. The pond and swamp factor, what percent of your watershed is a pond or swamp? And if you have no ponds or anything like that, then there's no reason to put that there. You want to add that in if that pond or lake is maybe a pretty reasonable size and takes up a pretty good size of the watershed and will make an impact. So I don't think I would put anything in here less than 1%. And then this is just the menu here that you select from with this drop down arrow. And then the storms that we have pre-selected here are the 2, 10, 25, and 100 year. You can change those to whatever you're particularly interested in. 2 year is sometimes we're asked for some information from an environmental department that's asking for flows that we would provide the 2 year flow for. And then the 10 years for the top and soffit on the culvert, 25 years for the channels or ditches or spread in depth, and then the 100 years for the culvert as well. And then sometimes the 50 year is useful because, well, not so much anymore, but we used to design bridges to 50 years. And then here's again, the inches, not the intensity, but the depth. And that's copied over from the earlier input that you did on the spreadsheet. And now we need to calculate or find what the initial abstraction is on for this one. And so we looked up the curve number earlier. To get the initial abstraction, this little comment is directing you to go to this worksheet right here. And I'm going to blow this up for you a bit. Again, this is copied out of the TR-55 manual. The curve number in this blue section is copied over from a previous entry, and 70 is the one that for our project. And we've calculated a 70, so the initial abstraction for that will be 8.57, excuse me, 0.857. Coming back to our worksheet, we would type in 0.857. It's copied across automatically for us. And then the next one, initial abstraction over perimeter, we're okay there. That takes place automatically for us. Again, we need to go and calculate, see worksheet 4B now. And we go to 4B. This one's a little tricky. This formula right here is what's going on in these calculations. And boy, you pound that out in your calculator a few times and you get tired of doing that real quick. So we need to, what we do is come down here, we'll delete these numbers. And this is what it'll look like when you're working through your spreadsheet. And the rainfall type is 1A. So you select the chart here by rainfall type. And we'll go to chart 1A. And then the time of concentration was 0.22. And now we have the 2-year storm is 0.21. So the 0.2 on the rainfall type here falls between 0.21 falls between 0.2 and 0.25. So we would use this area here, this cell. Use the equal sign and come up and select the 0.21. This is rounded off, and there are a lot more numbers following the 1 that you want to include in the calculations. If you just type in 0.21 here, it won't give you the right answer. Following this across, the correct answer you're looking for is 113, and then the answer we'll type in here is 113. Coming to the next one, 0.17 is in between 0.2 and 0.1, so we'll just come here, equal sign, 0.17, and then over here the answer is 127, and then 12, we'll do that again, and the answer is 143. And then finally, the last one is 11. Enter, and then 149. There are occasions where you might end up with the same number, like 0.11, for example, might be the same number all the way across 2 or 3 of these columns. That's not unusual. So if that happens, then just continue to use that in the calculations. So once you've filled in these cells right here, then we go back to our worksheet, and that has filled in the answers for us across here. There's a quick check here to make sure that it's okay. And what this is doing, like I explained on the very first summary sheet, it's plotting it on a graph. And if it can't find it on the graph, then it goes to some default values. And if it does go to those default values, it just gives you an alert here. That's not horrible. It doesn't mean you have to throw out the calculations. It's just information you should know. And then lastly is the pond and swamp factor, selected from here. And here is the table that you're selecting one. Here's the percent of pond and swamp factor and and what you'll use. And then select the appropriate one. And then here's the final answer for us. And these answers are the ones that are actually copied over to the first summary spreadsheet, which would be 0.59 here. That's the answers in at it. And that would, well, that's it. That's how we get through TR-55. I've showed you how to use these two assistants for your calculations. What I like to do is when I get the soils data is I build a soil sheet that looks like this. And then I copy what I need, what the appropriate soil um, for my watershed. I just copy those over to my worksheet here, or excuse me, here. And I just copy those over here. And then I let this one ride with all the copies of my spreadsheet as I go through and do each system. And then it just becomes a convenient copy and paste. And then finally, there's that rainfall type map that I added in there for your convenience. And I think that covers it. I think that's it. We're all done. And with that, I'll go ahead and stop sharing and see if there are any questions.